Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 10, and today we're looking at Section 10.6 on alternating series and conditional convergence. All right, an alternating series is a series in which the terms are alternately positive and negative. That sounds logical enough. And it turns out it's pretty easy to determine whether an alternating series converges. So this is called the alternating series test, or Leibniz's test. The series n equals 1 to infinity of -1 to the n plus 1 times u sub n, which is u1 minus u2 plus u3 minus u4, et cetera, converges if all three of the following conditions are satisfied. Number one, the u sub n's are all positive. That's kind of a legal loophole just to make sure that the series is really alternating. Number two, the positive u sub n's are eventually non-increasing. In other words, u sub n is greater than or equal to u sub n plus 1 for all n greater than or equal to some integer capital N. And finally, u sub n is approaching 0. The limit as n increases without bound of u sub n equals 0. So really, as long as you know your series is alternating, you just have to check that the absolute values are decreasing and approaching 0. That's pretty much all it takes. All right, here's a picture. The partial sums of an alternating series that satisfies the hypotheses of the theorem we were just looking at. For n equals 1, straddle the limit from the beginning. So starting at 0, you add the first term and then subtract the second term and then add the third term, subtract the fourth term, and you see where the partial sums end up, and they keep falling alternately above and below this number L, which turns out to be the limit. All right. And eventually they will get as close to that limit as you want, as long as you go out far enough. All right, next we have the alternating series estimation theorem. Unlike other types of series with all positive terms, it is pretty easy to estimate the sum of an alternating series. If an alternating series satisfies the three conditions of the previous theorem, then for n greater than or equal to some integer big N, S sub n equals u1 minus u2 plus u3 minus u4, et cetera, up to -1 to the n plus 1 times u sub n, approximates the sum L of the series with an error whose absolute value is less than u sub n plus 1, the absolute value of the first unused term. Furthermore, the sum L lies between any two successive partial sums S sub n and S sub n plus 1, and the remainder, L minus S sub n, has the same sign as the first unused term. So there's quite a lot to digest there, but really the highlight is the error in estimating the sum of the series with the first n terms is going to be smaller than the absolute value of the n plus first term. All right, so now we'll look at these examples. In the first two examples, we will determine if the alternating series converges or diverges. In the next example, we will estimate the error involved in using the sum of the first four terms to approximate the sum of the entire series. And finally, we'll determine how many terms should be used to estimate the sum of the entire series with an error of less than 0.001. So switching over to the tablet. All right, so here's the first example where we will determine whether this series converges or diverges. Notice that it is an alternating series. As we've talked about before, -1 to the power n or to the power n plus 1 is what gives you the alternating signs. So to check the first condition of the alternating series theorem, you just have to make sure that the other part of the term is always, well, technically could be always positive or always negative. It's usually going to be always positive. And for, well, that thing is always positive. We don't even have to think about the sign of natural log of n because it's being squared. 4 over the square of natural log n is definitely always positive. So now we just have to ask, is 4 over natural log n squared decreasing? And I think it's pretty clear that it is, because natural log n is increasing. I would be happy with that explanation. All right, and then finally, is 4 over natural log n squared approaching 0? Well, yes, it is, because natural log n is approaching infinity. So the conditions of the alternating series theorem are all met, and this series converges by alternating series theorem. All right, like I said, very easy theorem to use, very easy test to use. All right, next we have the sum n going from 1 to infinity of -1 to the n times natural log of 1 plus 1 over n. Okay, so the first question is this thing here always the same sign? Well, yes, it is always positive. Natural log of x is positive for x greater than 1. And 1 plus 1 over n is always going to be greater than 1. It starts off at 2 when n equals 1. You have 1 plus 1 over 1. And then the inside of that natural log function does start to decrease, and it's approaching 1, but always staying greater than 1. Okay. So the next question is natural log 1 plus 1 over n decreasing? And the answer is yes. Because 1 plus 1 over n is decreasing. All right, and the last question is natural log 1 plus 1 over n approaching 0. And again, the answer is yes, because the limit as n increases without bound of natural log 1 plus 1 over n, as n increases without bound, 1 plus 1 over n approaches 1. So this limit is equal to natural log 1, which is 0. So the answer to that question is yes. And because all three conditions of the alternating series theorem are met, this series also converges by the alternating series theorem. All right, the next example was to estimate the error when this series is approximated using the first 4 terms. All right, error in using first 4 terms to approximate sum of series. All right, well, by theorem 15, the error in using the first four terms to approximate the sum of the series is going to be no greater than the absolute value of the fifth term. Okay, so the absolute error is less than 1 over 10 to the fifth, which is 0.00001. So that would be a pretty good estimate. And in fact, I went ahead and because this series happens to be geometric, we can find the exact sum of the series. Normally we can't do that. So just notice what I did here. So first I have the sum of the first four terms, which is 0.0909, exactly 0.0909. The sum of the entire series, as I mentioned, it is a geometric series. A is 1/10, R is -1/10, and that comes out to 1/11, which is 0.090909 repeating. So the difference between the sum of the first four terms and the sum of the entire series is 0.0000 and then 09 repeating, which is just a little bit less than 0.00001. All right, so that worked. Normally we won't be able to check it like that, but in this case we could because it's a geometric series. Okay, and in this example, it said something like how many terms must be used to approximate the sum of the series with error less than, I think it was 0.0001. Okay, I will double check. Okay, I'm glad I checked. It was actually 0.001. So let's fix that real quick. 001. Okay. So basically what we need to do is we need to figure out what is the first term of this series whose absolute value is less than 0.001. And I'm going to do that on the calculator. All right, so what I'm going to do is in my y equals screen, I am going to put x over x squared plus 1. Uh-oh, that's not going to work. X over x squared plus 1. All right, and then I am going to set up my table so that it starts at 1, and for now it's going to go up by ones. Now, and then what I'm going to do basically is just scroll through the table and see when does it first go below 0.001. Now, if it turns out that 1 is too small an increment, it's taking too long, I can always come back and bump it up to something else. All right, so now let's look at the table. So we're looking under Y1 to see this go below 0.001. And actually it doesn't look, 001. Yeah, that might take a little while. It doesn't even go below 0.01 until you get to just 100 terms. All right, so let's go back to table settings. And let's try making the increment 100. All right, and then we'll see how that goes. So, okay, we want it to go below 0.001. So scrolling, scrolling, scrolling. Okay, we're getting close. Okay, so right around 1,000 is, well, somewhere between 990 and 1,000. Okay, so just to make sure we've got exactly the right value of n, I am going to go into table settings one more time. And I'm going to start at 990 and put it back down to 1. Okay, I guess I had the increment set to 10. I meant to set it to 100, but anyway, that worked out. Okay, so yeah, look at that. When n is 999, n over n squared plus 1 is just a little bit more than 0.001. And when n is 1,000, it's just a little bit less than 0.001. So we can say something like this first happens when n is 1,000. Okay, so if you want to estimate the sum of this series with error less than 0.001, then you would need 999 terms, and your error will be less than 0.001. All right, back to the presentation. Okay, so at some point I got curious about what was the exact sum of this series, so I went into a piece of software that I thought might be able to tell me. And it turns out there is really no nice closed expression for the sum of this series. It has to be written using a bunch of functions that I don't remember what they mean, if I ever knew. But anyway, there's the first however many decimal places that is. So yeah, just again, I was interested, so I looked into it. All right. All right, so that brings us to conditional convergence. A series that converges but does not converge absolutely is called conditionally convergent. We say that it converges conditionally. And conditionally convergent series have some interesting properties that we'll talk about here in a little bit. All right, so as an example, let's look at which of the following series converge absolutely, which converge, and which diverge. All right, 2 examples there. So we will go over to the tablet. All right, so first let's figure out if this series converges absolutely. So look at the absolute value of a sub n, which is 1 over 1 plus the square root of n. All right, so in other words, we're looking at the series 1 over 1 plus the square root of n. Okay, so if you think back to all of the other tests for convergence we've used, nth term test, geometric series, telescoping, integral test, comparison tests, I'm thinking that this one should be good for comparison test. It should do the same thing as the series 1 over the square root of n, because as n gets large, that plus 1 in the denominator is going to become sort of insignificant. We know that this series is a P series with P equal to 1/2, which is less than or equal to 1, and therefore diverges. Unfortunately, I'm not going to be able to use the direct comparison test because 1 over 1 plus the square root of n is less than 1 over the square root of n. So I'm disappointed about that because that means the inequality is going the wrong way for direct comparison test. So what I do in that case is I use the limit comparison test. So we'll make this a sub n, we'll make this b sub n, and we'll look at the limit as n approaches infinity of a sub n over b sub n, which is the limit as n approaches infinity of 1 over 1 plus the square root of n, divided by 1 over the square root of n, which is the same thing as multiplying by the reciprocal. And I think what we can do here is use our Calc 1 shortcut. This is not technically a rational expression because square root of n and 1 plus the square root of n are not polynomials, but they still act like polynomials. You can still talk about dominant terms and leading terms and all that stuff. So as n increases without bound, the limit of this expression is going to be the ratio of the quote unquote leading coefficients, which is 1 over 1, which is 1. 1 is finite and positive, and therefore this series and this series do the same thing. And since we know that this series diverges, that means this series also diverges. All right, so what's happened at this point is that we know that the absolute value series 1 over 1 plus the square root of n diverges, which means that the original series does not converge absolutely, okay? However, it may still converge. So now let's go back to the alternating series and going from 1 to infinity. And I think this was a -1 to the, oh, to the n, huh? Okay. All right, so now we'll use the alternating series test. Okay. Clearly 1 over 1 plus the square root of n is always positive. 1 over 1 plus the square root of n is clearly decreasing because the denominator is increasing. And 1 over 1 plus the square root of n is definitely approaching 0. All right. So the alternating series does converge by the alternating series test. And since it does not converge absolutely, they didn't exactly ask me this, but I'll go ahead and say it anyway. Since the original series does not converge absolutely, that means that the alternating series converges conditionally. All right, next example. The sum n going from 1 to infinity of -1 to the n plus 1 times the square of n factorial divided by the square of the factorial of 2n. All right. Okay, well, with all those factorials, this is definitely a candidate for the ratio test. And the great thing about the ratio test is that it will nail down. I mean, if the ratio test works, that means that the series converges absolutely. Okay. All right, so we're going to look at the limit as n increases without bound of the absolute value a sub n plus 1 over a sub n. And what that absolute value is going to do is knock out the alternating sign. All right, so when we replace n with n plus 1, we're going to get n plus 1 factorial squared over 2 times n plus 1 factorial divided by a sub n. And again, I will multiply by the reciprocal. All right, so let's see what we have. We have n plus 1 factorial, n plus 1 factorial. It'll be easier to simplify if I, just write it as times itself instead of squared. 2n plus 2 factorial. And then 2n factorial, and down here I'll write n factorial, n factorial. All right, so as we've discussed before, n factorial into n plus 1 factorial leaves n plus 1. So same thing here. All right, and then 2n factorial divided by 2n plus 2 factorial. All those factors cancel except for the first two factors in 2n plus 2 factorial, which are 2n plus 2, 2n plus 1. All right, so we are left with the limit as n increases without bound of n plus 1 times n plus 1 over 2n plus 2 times 2n plus 1. That is a rational expression. The leading term upstairs is n squared. The leading term downstairs is 4n squared. So the limit of this thing is 1/4, which is less than 1. Therefore, the original series converges absolutely by the ratio test. Now, I don't know exactly how these questions are set up on your online homework, but I did notice that the directions say which series converge absolutely, which converge, and which diverge. So depending on how it's set up, you might also have to select converges. Remember that every series that converges absolutely also converges. And so this might have two answers depending on how it is set up. All right, so now we'll just wrap this up with a couple of interesting facts about conditionally convergent series. First, we have the rearrangement theorem for absolutely convergent series. If the sum n going from 1 to infinity of a sub n converges absolutely, and b1, b2, blah, 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 b sub n, blah, 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 is any arrangement of the sequence a sub n, then the series b sub n also converges absolutely, and it has the same sum as the original series. So in other words, if you have an absolutely convergent series, you can rearrange the terms of that series in any order you want, and it will still converge absolutely, and it will converge to the same sum. And this is not true for a conditionally convergent series. In fact, the terms of a conditionally convergent series can be rearranged to converge to any number you want it to converge to, or even to diverge. There may be a problem in your homework where you get to play with that. So I will leave that for you to play with. I'm not positive that there is, but there might be. All right, and we have at this point pretty much reached the end of all of our tests for convergence. So let me just go over this with you real quick, and I'll talk a little bit about, what would be a cue to use this test or another test. So first we have the nth term test. If a sub n approaches anything other than 0 or doesn't approach anything, the series diverges. So unfortunately, this test doesn't work very often because most of your series a sub n will approach 0. But if you happen to look at the series and you think that that limit might be something else, you should try the nth term test first. Remember, if it turns out that that limit is 0, then that test does not work. All right, you have to try something else. Then we have geometric series. A geometric series converges if the absolute value of r is less than 1. Otherwise, it diverges. Remember that with a geometric series, you can actually find the exact sum. P series, we use those a lot with our comparison tests. The sum 1 over n to the p converges if p is greater than 1. Otherwise, it diverges. All right, for series with non-negative terms, try the integral test. Well, I don't actually agree with part of this. The integral test or comparison tests. Ratio test and root test actually work even with series with non-negative terms. I think this might be a holdover from a previous edition of the book. So I would say series with non-negative terms, try the integral test or a comparison test. Series with some negative terms, does the sum of the absolute value of a sub n converge? If it does, so does the original series a sub n, since absolute convergence implies convergence. And you can use the ratio test and the root test on series with some negative terms. And finally, if your series is alternating, it should be very easy to use the alternating series test, like we went over in this section. So that's going to do it for section 10.6, and we'll see you next time.